Hello and welcome. So in today's lecture, we'll be looking at our first policy gradient reinforcement learning algorithm that is known as reinforce. So essentially this is a Monte Carlo policy gradient method. So what we'll be doing in this lecture is we'll be making use of the results from the policy gradient theorem, which we derived in the previous lecture, and see how we can actually sample in a way that approximates the expression that's actually given in the theorem. So actually having said that, let's get started. So the first thing is let's write the result that we got from the previous lecture, where we said the derivative of some performance measure that we denoted as j theta is proportional to the summation over all states of d pi of s, our stationary distribution, times the summation of all actions of q pi s comma a times the derivative with respect to pi of a given s parameterized by theta. So what we said was the stationary distribution, essentially it represents the weights that we put on each of our states. So if we visit a state frequently in the long term, then it deserves a higher weight and vice versa. Q pi s comma a, you know what that is. And pi a given s is just the probability of taking an action in a given state, which you should also know. And we're just taking the derivative of that. So in case you're wondering where all of this actually came from, well, what we're doing here is just, you can look at the previous lecture because that's where we actually looked at the policy gradient theorem and how we actually derive it. But just to summarize here, what we're doing is that we wanted to get the gradient of this performance measure so that we can actually update our theta value, right? Because essentially we're saying we would update theta at time step t plus 1 to be equal to theta at time step t plus the derivative of j theta, right? So this was essentially our gradient ascent update rule. And here we're just looking at the term, the derivative of j theta, and how we can actually compute it. So written another way, this is an expectation under pi of the summation of all actions of q pi s comma a times this other term here, right? And right now we say it's an expectation because we're doing it over our states, right? But for a proper expectation, we need to say, okay, what is the weight for each state? And we also need to compute the weights for each actions as well, right? So what we can do with this expression is we can multiply it and divide it by pi a given s, right? So we write it as so, like, we write it like so. Expectation under pi of summation over all a, pi a given s, q pi s comma a, derivative of pi a given s parameterized by theta divided by pi a given s parameterized by theta, right? So we look at this expression. So what do we see? So we see that essentially it's the same as what we have here, but we just multiplied and divided by the same term. And the reason we did that is that when we're computing the expectation here, we just incorporated the states, so like the weight of each state, but we also need to incorporate the weights of each actions, which is given by this term. So essentially, this is an expectation over pi of the summation onto all actions of q pi. So this term is essentially absorbed by the expectation. So we'll end up with q pi s comma a times the derivative of pi a given s parameterized by theta over pi a given s parameterized by theta, right? So this is essentially our expectation. So the reason why we're computing this expectation, because this expectation is over all the states and over all the actions, over our policy essentially. And we need a way to actually sample so that we can make our update here over there, right? because we're not going to be able to actually compute all of this at once, but we're actually going to be sampling and updating our data and so on, as we do in any stochastic gradient method. So now the idea here is that, okay, we can actually write this as theta at time step t plus 1 is equals to theta at time step t plus alpha times, so we're going to sample here, and the way we're actually going to sample is we're going to take our term here, q, let me write it like this, st, comma, at, right, which is our q value here, and we're essentially going to divide this by pi at given st parameterized by theta t times the derivative of pi at given st parameterized by, again, theta t. So we just took a sample essentially from here. So this q is the one that's given here, the denominator is what's given here, and this numerator is what's given over there. So that's how we make our update. So you can actually think of it as this is theta t plus some learning rate times some coefficient here, right? That's expressed by these terms, right? Multiplied by the derivative with respect to pi. The fact that we're taking the derivative with respect to our policy is essentially why we're calling this like policy gradients, right? And then so normally we would update our, let's say, our theta by saying it's equal to theta t plus alpha times some gradient, but it's just that we're multiplying by this coefficient, right? So that's essentially what we have. So when we're talking about reinforce, essentially this qt, st, at is usually equal to gt since it's a Monte Carlo method. So this is usually gt. So right now I'm writing it in this way, but you'll see me like changing it up and actually writing the full return gt instead, right? And you'll see that when we look at the pseudocode. So something interesting about this expression here, because we have this, fine, we have this derivative we're taking, but this coefficient of the q values over the policy, it actually does something special in our updates, and it balances exploration and exploitation. And the way it does that is, say for high values, if we have high q values, high values of qt, st, at, right? So this is showing that we have, let's say, high action values, right? So what the algorithm does is, if this value is high, right, that means this entire coefficient is high. So that means the algorithm adjusts theta t so that the probability of taking such action is increased, right? So when we have these values, the probabilities of taking this kind of actions that are high is increased. And essentially, this is actually doing exploitation. We're exploiting the high values that we have. But at the same time, if we look at our denominator here, which is the probability of taking an action given when some state, if this probability is low, this entire term is going to be higher. And once more, this is going to increase the probability of us taking that action, right? So even before, if the probability itself was low, because this entire term is high, when we update our data, that means the probability of us taking this action is also increased, right? So that's how it tries to balance the exploration and the exploitation. So that's just an interesting result. However, you'll also find that at times we can actually express theta t plus 1 to be equal to theta t plus, let's say, alpha times, and then you'll find something like ln, oh, not that, you'll find the derivative of ln pi at given st, which is parameterized by theta t, multiplied by qt, not qt, this is q pi st, comma at, right? So you might find it in this manner, right? or it could be just, this term essentially could be GT. Like I said, in the case of reinforced, this term itself is GT, which is just a return. So we can write it in that way. So you could find it expressed in this way sometimes, this update. And the reason why we can actually express it in this way, so this is just another way of expressing the same thing, right, over here. So the reason why we can do that is because, well, we know from calculus that the derivative with respect to x of ln x is equals to the derivative of what's inside, which is 1, divided by the original term itself, x, right? So it's the derivative of what's inside over, like, the full term x. So in our case, when we take the derivative, let me use a different color for that. When we take the derivative of ln pi a given s parameterized by theta, well, this is equal to the derivative of what's inside, which is the derivative of pi a given s parameterized by theta over the original term, which is pi a given s parameterized by theta. Right, so you might see it written with an ln in this way, and the reason for that is that, well, this over this is essentially our ln, right? So this over that is our ln here. So now you can see like why we can write this term in terms of logarithm sometimes, and you'll see that at times. So, and that's fine. So having said that, so now we know how we actually make our update when we're doing our reinforce algorithm. Let's actually go through the pseudocode for this, right? So let me open up a new page. So we're gonna look at, going to look at reinforce pseudocode. So essentially, we start with our initialization. So we have our parameterized function pi a given s, which is parameterized by theta, right? We have this. We initialize that, and what is our goal? Optimal policy maximizing j theta, which is why we take the gradient with respect to this and add it to our theta, because we're doing gradient ascent, which is maximizing this value. Okay, so everything else is pretty standard, right? So for each episode, do the following, and then we select S0, our initial state, right? And we generate an episode following pi, which is parameterized by theta t, right? So we select an initial state S0, then we generate an episode from S0. So we end up with something like, we start at S0, action A0. Okay, let me use a different color for this to be clear. So we start from S0, take action A0, we get a reward R1, and so on until we reach state ST-1, where we take action T-1, and we get our reward RT, our final reward. Right? Now for t is equals to 0 until T-1, what are we going to do? We're going to do an action value estimate, right? Q time step t of st, comma, at, right? Which is essentially, so that's q at time step t, right? Oh, which is why I was using t there, but anyway, which is equals to the summation from k is equals to t plus 1 up to t of gamma k minus t minus 1 of rk. So you can see that this is essentially the return, the discounted cumulative rewards, which we call the return essentially, which is why I say we can just think of this as our GT in this case, right? So maybe we can continue in that way. And then we update our policy parameter, update, right? And the update rule is theta t plus 1 is equals to theta t plus alpha times the derivative with respect to theta of ln pi at given as t times q, oh, let me just write times gt instead to make it simpler, right? Times our return, the return that we computed here, right? I'm just writing the times gt here. Okay. And as you can see, this update is essentially the same as what we had over here, right? The thing that we computed. Okay, that is fair and fine, right? This is how we make our update using reinforce, right? So let's actually look at a couple of points here. Right? How are we actually sampling our actions, right? Because in theory, when we're actually sampling our actions, we must follow the distribution like pi a given s. That's the theory that we looked at before. And that would actually make this algorithm on policy, but the implementation will see that it's actually off policy. And I'm going to tell you why in a moment now. So the first thing here we look at is we use pi theta t. We use this to generate the episode, right? So if we were to follow the theory, right, because here we use pi theta t to generate the episode, but at the same time, what we're doing is we update theta t plus 1, theta t plus 2, theta t plus 3, and so on, just from the samples we generated using. Because if you look here, select S0, generate episodes following pi theta t, right? And then using the episodes we generated, we're going to compute here theta t plus 1, theta t plus 2, and so on, just following this, right? So what this does, so this is using pi theta t, right? That's how we're making these updates. So the advantage of doing this is it uses samples efficiently, right? So the samples we're generating here, we're using them efficiently. However, it is, if we're actually to follow the theory itself, the way you are actually supposed to be doing it is to say, let's say, we're updating theta t plus 1, theta t plus 2, and so on, right? But we should update them with pi theta t plus 1, pi theta t plus 2, t plus 2, and so on, right? So this is what would happen if, let's say, we're following the theory. This is the theory, and this is the way we're doing our implementation, right? So as we can see, the way that we're doing our implementation and the way we would make these updates, if we're following the theory, are actually different. So this is more accurate, but it does not use the samples efficiently. This one uses the samples efficiently, but it is not as accurate. So the implementation itself is actually off policy, right? Because it is, while it's using the samples efficiently, it's not actually adhering to the policy gradient theorem itself. So there's a trade-off here between how accurate you want to be as per the theory and how efficiently you want to use the samples, right? So that's the trade-off. But having said that, I hope you actually get an idea of how this algorithm is working, um, how we derive it, what is the trade-off between following the theory and having it becoming on policy, and making use of the samples efficiently and having an implementation over here that's actually off policy. So there is a trade-off over there, right? But so the problems with this method, just like any Monte Carlo method that we've seen before, is that it has, as we would expect, high variance, right? It has high variance and it has slow learning, right? So that these are the essentially, if we ask, the disadvantages of this reinforced method, right? But it's a decent start, but again, we can do better than this. So the way we can actually try to tackle some of the problems that are introduced by this method is by introducing something known as a baseline, right? So we move on to our next topic, which is reinforce with baseline. Right, so that's what we do here. So what is a baseline, essentially? Well, I'll explain it in a moment, but essentially we're rewriting our j theta to be proportional to, same thing as before, we have our stationary distribution here, and over all actions of q pi s comma a minus bs, which is our baseline, times the derivative with respect to pi of a given s parameterized by theta, right? So the baseline essentially can be any function that does not vary with a, does not vary with our action space, right? And the thing is, after we add this baseline, we actually need to ensure that we did not damage anything in this theorem, that the results are still the same, that this entire term is still unbiased, right? And the way we do that is by looking at the expectation with the added term and ensuring that it's the same as the expectation from before, right? So the way we'll do that is say by saying, okay, let me use a different color for that. So let's say expectation over a of our baseline s, right? Let's say we have b of s here, times the derivative of pi a given s parameterized by theta, right? This is equal to, so since this does not depend on a, we can take it outside. So we have bs, right? And then the summation and the gradient operation, we can switch them. So we have the gradient of the summation over a of pi a given s parameterized by theta, right? So the summation over all actions of the probability of a given s, well, it's 1, right? Because the probabilities must sum up to 1. So this is equals to bs, the derivative of 1, and this is equal to 0, right? So that means as long as the baseline we add does not depend on our action, then when we compute our expectation, it will still remain the same, right? That's why that's what this proof here is showing, right? That it would still remain the same, right? So the way we would actually make our update when we're doing reinforce with baseline is say theta times step t plus 1 is equals to theta times step t plus our learning rate alpha times jt minus bst, which we can add as long as it doesn't depend on our actions, times the derivative with respect to pi of at, st parameterized by theta t divided by pi at, st parameterized by theta t. So what did we say? What did we learn from here? That the baseline itself, it leaves the expectation of our update unchanged, right? And that's why we did this proof over here. But the reason why we added is because it lowers the variance, right? So the baseline can help in lowering the variance because one of the disadvantages we mentioned with this method of reinforce is that it has high variance, but if we incorporate a baseline, it can help us in lowering the variance. So for example, let's say we have states in which all action values are high. So we may need a baseline to differentiate the higher valued actions from the less higher valued ones and vice versa, right? So that's what we can do. So you might think to yourself, like, what is an example function that we can use as a baseline? Well, one choice for a baseline, so one choice for a baseline can be the state value, right? V of st parameterized by w, right? So the theta is with respect to the policy, the w is with respect to the value function. So what does this change in our update? So I'm not going to rewrite like every element of the pseudocode that we did here, but let me just rewrite the important parts because everything else is the same. But the difference is, okay, fine. First, we're going to compute our return g as usual and say it's the summation from k is equals to t plus 1 up to a capital T of gamma k minus t minus 1 of rk, right? That's what we said before. And then we're going to compute delta here, which is equal to g, right, minus our baseline, which is v of st comma w, right? So before, when we're doing our update rule, we're just computing, if you look here, we're just computing our gt here, right? Oh, here is using q, but same thing. And then multiplying this expression by gt. But now that we're using the baseline, we're going to be multiplying that term by g minus v of st comma w. But now we have two things. So our value function, which again, we looked at function approximation already. So we already know like how we make our updates. But we essentially have two weights to update. We have w and we have theta, right? So the first thing we want to update here is w. And we update it by saying w is equal to the old w, the same way we were doing it when we're looking at function approximation. But anyway, plus plus the alpha with respect to w times delta, right? Because we want to essentially maximize this. So the derivative with respect to v of st comma w, right? And we update our theta by saying it's theta plus alpha, alpha with respect to theta, the learning rate for theta, times whatever our discounting term is, times the delta that we computed here, the derivative of ln pi at given st comma theta, right? So the idea here is we want, the main idea you should just capture from this anyway, is that we added a baseline and now we update our weights w, right, with respect to v, and we update our weights w for our value function, and we update our weight theta for our policy here. So that is it. So having said that, this essentially covers the idea behind why we add a baseline. So the final thing I want to talk about is what is known as actor-critic methods. So here I'm just going to introduce what they are, and then in the future lectures we're going to look at some reinforcement learning algorithms that are actually making use of this, right? So I'm just going to Actor-Critic methods. So that's what we're going to talk about. So, okay. So the idea here is we're doing the same thing as before, but we want to use the value function as a critic. So when we're doing reinforce with baseline, the value function was acting as a baseline, right? And not a critic, right? So the question now is, what is a critic, right? So what it is to be a critic, it means we're using our value function estimate for bootstrapping. So when we're looking at reinforce, we saw that we're doing sort of like Monte Carlo, but for policy gradients. Now, when we're looking at Actor-Critic method, it's almost like we're doing something towards like TD learning, but for policy gradient methods. And we have this thing called a critic that is essentially our value function that's doing some bootstrapping. That's the idea behind Actor-Critic methods. So, okay. So let me write this down. A critic means using our value functions or value function estimates, let me say instead, for bootstrapping. So as before, we know that with bootstrapping, we're introducing some bias, right? Because we said reinforce with baseline, it's still an unbiased method, right? Because the baseline we added does not depend on, it does not actually affect our expectations. But when we're doing now Actor-Critic methods, when we start adding bootstrapping, it introduces bias, but we have already looked at the advantages of doing that, or of bootstrapping itself, in that it actually reduces our variance as well, and it helps us accelerate learning. So it's almost analogous to when we're looking at Monte Carlo versus TD methods. It's almost like we're doing the same thing again. So let's actually look at how we would do one-step Actor-Critic methods, or almost functioning like TD0 in a way. So the way we would do that is to make our update, theta t plus 1 is equals to theta t plus alpha. So we're replacing of our complete update. So here we've got gt up to t plus 1 minus vst comma w. We're replacing our full return with the bootstrap estimate, right? So all of this is essentially the same as what we were looking at before. So we have pi at given st parameters by theta t, right? So if you look at this expression, it almost looks like what we're looking at when we're looking at reinforce with baseline. So what we do here is we say, okay, instead of we're just taking the one-step return, which is essentially our t plus 1. So let me use a different color for this actually to make this clearer. Actually, let's write it from here. Equals to theta t plus alpha times. So instead here, we would have our t plus 1 plus gamma v of st plus 1 parameterized by w minus v st parameterized by w. Actually, let's do it like that. Yeah, much better. Right, so this over here is just representing this. So instead, before, when we're looking at reinforced with baseline, we had the full return, but now we just have the bootstrap estimate, right? Like the same way we'll do when we're looking at TD0. So this should be straightforward. So that's the derivative with respect to pi of at given st parameters by theta t divided by pi at given st parameters by theta t, right? So yeah, that's the idea behind Actor-Critic methods. So I just wanted to give you an idea of what they are and how they are different from when we're looking at reinforce with baseline. And why we say reinforce with baseline is not an actor-critic method, since it only uses the baseline or value function here as a baseline. It only uses this value function as a baseline. But in actor-critic methods, this value function is also used for bootstrapping, and that's why it's denoted as a critic. So now you can have an idea of what the differences are. So having said that, I think I can end our lecture here. So in the next lecture, we're going to start looking at more policy gradient algorithms that are being used recently, and see if we can apply, say, one of them on our self-driving car agent. So having said that, I'm going to end the lecture here. So thank you for your time.